Once you've worked on what the idea of the derivative of a function is and practiced finding the derivatives of a lot of different types of functions, you're ready to move on to applications of derivatives. Now, you may have already done some applications of derivatives with implicit differentiation and the related rate problems. Certainly with finding the slope of a tangent to the curve with your formula from your derivative, and then using that to write the equation of a tangent line. And also the extreme value theorem is kind of an introductory of the application of derivatives outside of our basic definition that we start with. Our next application of derivatives is something called Rolle's theorem. And Rolle's theorem is this. Let f of x be a continuous function on a closed interval, and let it be differentiable on the open interval. So the derivative has to be defined also on the open interval. If f of a, the output at your left endpoint A, is exactly the same value as f of b, the output at your right endpoint B, then there is at least one number c in the open interval between a and b, such that f prime of c, your derivative evaluated at that c, would come out to be 0. So when we're doing work with Rolle's theorem, we always want to make sure that all of the conditions of Rolle's theorem are met, and then go find the values of c guaranteed by the theorem. Let's look at an example. So here we have determine if Rolle's theorem applies to f of x equaling x to the fourth minus 2x squared on the closed interval from -2 to 2. Remember, brackets means that you include the endpoint, so that's a closed interval from -2 to 2. And if so, find the values of c guaranteed by the theorem. So when we look at this, we want to keep looking back at what Rolle's theorem says and to verify that we're going through the whole process. So determine if it can be applied. So first of all, look at your function f of x. It's equal to x to the fourth minus 2x squared. And it's on this closed interval, -2 to 2. Well, this is a polynomial function. And polynomials are continuous throughout the entire real number line. So certainly it's continuous on this closed interval. So since it's a polynomial, so it's continuous throughout the real number line, so definitely on the closed interval. Next, we want to make sure that this function is differentiable on the open interval between -2 and 2. Well, our derivative f prime of x is 4x cubed minus 4x. Can't see that 4 through my loop of my G. There we go. Now, this derivative is also a polynomial. So the derivative is defined throughout all real numbers. So certainly it's defined on the open interval. So for the function to be differentiable, you need that your derivative of your function to be defined on that interval. So here we have our derivative. It's defined for all reals. So f of x is differentiable. Definitely through all real numbers, so on the open interval. Next up, for Rolle's theorem, we have to check that f of a is equal to f of b. So a is your left endpoint, so we're going to evaluate the function at the left endpoint. So f, the function evaluated at -2, is -2 to the fourth minus 2 times -2 squared. Well, that's 16 minus, and then -2 squared is 4 times -2 is my -8 there. So 16 subtract 8 is going to give us 8. F of 2, the right endpoint, is 2 to the fourth minus 2 times 2 squared. So that gives me 16 minus 8 also, which is also 8. So the output at the left endpoint matches the output at the right endpoint. So we verified that part. So now we've verified all three parts. Rolle's theorem can be applied to this function on that interval. So we're guaranteed at least one C in the open interval. So in the open interval between -2 and 2, such that the derivative evaluated at the C, it comes out to be 0. So we want to look at our derivative and we want to put C's in wherever the X's are for the left-hand side of our equal sign. So look at the derivative. F of C is 4C cubed minus 4C is equal to 0. Now this we can solve by factoring. It's equal to 0, so we look at a greatest common factor. We have a greatest common factor of 4C. Our C squared minus 1 can factor is C plus 1, C minus 1. So 4C times C plus 1, C minus 1 equal to 0. Set each factor that has a variable in it equal to 0 and solve for C. So I have 4C equals 0, 4C plus 1 equals 0, 4C minus 1 equals 0. Divide both sides by 4, I get C equals 0. Subtract 1 from both sides, I get C equal -1. Add 1 to both sides, I get C equal 1. As a last thing, I need to make sure I only report the C values that are in the open interval between -2 and 2. 0's between -2 and 2, -1's between -2 and 2, and 1's between -2 and 2. So we will report all three of these values of C. So we've then found the C's guaranteed by the theorem. Now I want to caution you that if you were doing a different question and maybe one of the C's would have come out to be either -2 or 2, you wouldn't report those because it's only the C values in the open interval that we report as the C's guaranteed by the theorem. So there you have it. There's an example of Rolle's theorem.